transition is from the benthic oxygen isotope record that shows us that the glacial interglacial pacing has changed over this time. And so a lot of this comes from this really seminal paper by Lorraine Lisicky and Maureen Ramo, also called LOR4, which looks at the benthic oxygen isotope from 0 to 1.5 million years. And shows that we see this change in glacial interglacial pacing over this time. And I think what was really seminal about this particular work is that it looked at 57 globally distributed benthic oxygen isotope records to kind of get a sense of what the pacing was of global climate. And it has since been updated. If you don't know, ProbStack, this was a student that worked with Lorraine and this was published in 2017. And as we get more records and as we improve some of our statistical techniques, we can start to have better alignment, and we can start to see the variability that we have among these records. And so if we think about the mid-Pleistocene transition, nominally we sort of think of it starting at around about 1.2 million years and completing around 600,000 years ago. And we see that the pacing of the glacial interglacial variability seems to go from 41,000 years, so dominated by changes in tilt, to 100,000 years in the late Pleistocene, and presumably dominated by the eccentricity cycle. And one of the things that we know is that because incoming orbital variation didn't, or the amount of incoming orbital forcing didn't change, there must have been feedbacks within the climate system that amplified the glacial interglacial response to the incoming orbital solar insolation. There's one thing that I want to point out, which is this 900 kiloyear event that seems to be important during the mid-Pleistocene transition as well. And there's kind of these broader conversations about whether or not the mid-Pleistocene transition was abrupt or whether it was gradual. And so we can see some features in the benthic oxygen isotope where we seem to see an increase in the benthic oxygen isotope, which would sort of imply that the transition was gradual. But we also have these things like the 900 kiloyear event, or even marine isotope stage 16, which makes us think that the mid-Pleistocene transition was more abrupt. And this is really important because it helps us identify some of the mechanisms that might have been important for the mid-Pleistocene transition. So some that have been proposed is CO2 related, so gradual cooling, global cooling. Other things that have been proposed that might be more abrupt would be changes in ice sheet dynamics. So going from slippery to more sticky ice sheets in the Northern Hemisphere, or going from marine-based ice margins to from terrestrial-based ice margins to marine-based ice margins in Antarctica. And some other things that might be related to either of those factors is thermohaline circulation reorganization, because those high latitude processes, cooling, ice margins, are really important for how we think about deep ocean circulation, how it forms, and how it moves around the globe. And so just to kind of step back in terms of, it might feel a little pedantic, but one of the things that we know from benthic oxygen isotope records is that they record the physical properties of the local water masses in which they live. So this is a figure from Sigmund et al. That I've modified, and all these little forams are living at the bottom of the ocean, and they're recording both the characteristics of these deep waters that form, so NADW in the North Atlantic, AABW in the South Atlantic, and the mixture of them into the Pacific, but also the spatial extent of these water masses. So it's kind of giving you two signals. It's giving you both the physical properties of the water mass itself, but also the spatial extent of those water masses. And so one of the challenges, if you're just looking at benthic oxygen isotope values, is that they record many different factors. So if we look at a benthic oxygen isotope value, the benthic oxygen isotope value itself is a reflection of the delta 18O seawater and temperature. And the temperature is a reflection of local signals. So which water mass is there? Global signals, are we in a glacial? Are we in an interglacial? And similarly for the delta 18U seawater, what is sort of the local salinity, for lack of a better way of describing it, signal, and what is the ice volume signal? Are we in a glacial, or are we in an interglacial? And so any benthic oxygen isotope value, if you're just looking at the benthic oxygen isotope value, is just some mixture of all these different components from local to more global signals. And so you have many possible interpretations if you're looking at a single oxygen isotope record. And I think that's one of the reasons that the LR4 stack was so transformative, is because you're basically averaging out these regional signals to come up with a global history of climate change. And so one of the techniques that we have that I use a lot is geochemistry of the shells itself and using minor elements. So in this case, you can use the magnesium calcium to isolate temperature within the carbonate lattice of a foraminifera. So essentially what you're able to do is you're able to couple the benthic oxygen isotope records to magnesium calcium based temperature reconstructions to then calculate what the delta H2O seawater component is. And so this is based on the temperature dependent magnesium substitution into the calcite lattice. So here you have magnesium calcium on the vertical axis, and on the horizontal axis you have temperature. And you can see that as temperatures increase, there's more magnesium that substitutes into this calcium lattice. So we can use that relationship to reconstruct temperature and then get out this delta H2O seawater component and start to understand a little, or start to decouple some of these local versus global signatures in temperature versus the delta H2O seawater. So if we think about the records that we have available to us, a lot of the records we don't have a lot. So there's three records that I'm going to be discussing for the rest of the talk. Mostly I'm going to be talking about these because they're high resolution and they're continuous. So there's one record from the North Atlantic, DSDP 607, and this was originally published by Cynthia Sosdian and Yaya Rosenthal, and I revisited this in 2016. And then there's a record by Harry Elderfield et al. In the Southern Pacific at ODP 1123. And then there's a record that I and Maureen did from the North Pacific, ODP 1208. And then I'm sure Alfredo will be talking about this, but there is a record that's available from ODP 1094. But the reason I'm not going to be talking about it for the in the rest of the talk is that it's not as continuous of record as I want for the further analyses that I do. But all of these different records are basically recording high latitude conditions, right? Because this is where these deep waters form. So they're recording both marginal characteristics from in terms of the interaction of sea and ice in terms of how deep water forms. So it's calculating the delta H2O of seawater in these regions and also the temperature of these regions when these deep waters form. So what exactly do these three records tell us in terms of what happened over the mid-Pleistocene transition? Well, because we only have three records, it turns out, and things are complicated because that's life, they actually tell us very different things. So the North Atlantic and the Pacific have different temperature histories. And if you take a strict interpretation of any of these delta H2O seawater records as an indicator of global ice volume, it would suggest that either there was no ice growth over the mid-Pleistocene transition, ice growth at marine isotope stage 22, or the 900 kiloyear event, or that there was ice growth at marine isotope stage 16. So because we have different histories from all these different records, there must be some regional issues or regional signals that we're recording in both temperature and the delta H2O of seawater space. So in the next few slides, I'm going to talk about what those different records look like and kind of the implications there and the interpretations we can make. So this is the first record. This is the North Atlantic record. This is from Cynthia Sosdian and revisited by myself. One of the challenges about this particular record is it's reconstructed from many different types of foraminifera. So Ambonatus, Willerstorfi, and Eubodrina were all used to reconstruct this record. So it's not a single species record. But that said, we do have relatively continuous temperature record here on this axis, going back in time from 0.5 to 1.5 million years ago. And then using this temperature record, we can then back calculate out the delta H2O seawater. And looking at this record, we see that we have a gradual bottom water temperature cooling in the North Atlantic. So that kind of favors these ideas about gradual CO2 drawdown in terms of a mechanism for the mid-Pleistocene transition. And then if we look at the delta 18O seawater, we see no large changes in delta 18O seawater over the mid-Pleistocene transition. So the original interpretation posed by Cyndia and Yair was that you had global cooling in the North Atlantic, and then there was no increase in ice volume over the mid-Pleistocene transition, or at least very little. If we contrast that with the records that we have from the Pacific, this is a record looking at benthic oxygen isotopes. This is just LOR4 from 0 to 1.5 million years ago. And I'm highlighting here marine isotope stage 16 and marine isotope stage 22, the so-called 900 kiloyear event. And so if we look at the benthic oxygen isotope records from the Pacific that we have, the first that I'm going to show you is from the North Pacific. This is from the Shatsky Rise. And we can see that there's kind of this gradual decrease in benthic oxygen isotopes. But the big step that we see in the benthic oxygen isotopes is here at marine isotope stage 16. So if we didn't know anything about temperature, we would assume that this is an event where we had cooling and ice volume growth during this time. And if we compare that with what's happening in the South Pacific, this is the record that was done by Harry Alderfield, we see that temperatures, or the benthic oxygen isotope record, is relatively stable. But instead of the marine isotope stage 16 that we see in the North Pacific, the big step in the benthic oxygen isotope is here at marine isotope stage 22. So already the benthic oxygen isotopes from the North Pacific and the South Pacific are telling us two different stories in terms of when changes happen during the mid-Pleistocene transition. So if we then use our magnesium-calcium based bottom water temperature reconstructions to calculate out what the delta 18O seawater is, here, this is a record that I did. It's based on Euvidrina, and it's pretty continuous. But the thing to note here is actually the bottom water temperatures don't change in the Pacific. They're near freezing for much of the record in the North Pacific. And we can look at the South Pacific as well, and we see a very similar story. The bottom water temperature records in the South Pacific are also near freezing through much of the mid-Pleistocene transition. So whereas in the North Atlantic, we saw that there was a 2 degree-ish bottom water temperature cooling over the mid-Pleistocene transition, both sites in the Pacific are basically having near freezing temperatures for most of the mid-Pleistocene transition. There's no broad trend in temperatures over this time. And then we can back calculate out the delta 18O seawater. So basically you take the temperature and then you take the benthic oxygen isotope to calculate delta 18O seawater. And what we can say is with the North Pacific record, what seems is that we seem to have two large excursions, one at marine isotope stage 22 and one at marine isotope stage 16. Interestingly, these are time periods when we actually have bottom water temperature warming, when we might, because it's a glacial, we might expect bottom water temperature cooling. But so we still have these large excursions in the North Pacific. But what we see overall for the mid-Pleistocene transition is that there seems to be an increase in the delta 18O seawater over the mid-Pleistocene transition that kind of finishes after marine isotope stage 16. So this would imply that there was some ice volume growth over this time period if we contrast that with what happened in the North Atlantic. We can look at the South Pacific record, and it has a different history than what's happening in the North Atlantic or North Pacific as well. So again, the bottom water temperatures are relatively flat. There's no apparent trend in bottom water temperature. They're near freezing temperatures. But then when we use the temperatures in the benthic oxygen isotopes to then calculate the delta 18O seawater, what we see is that the big step in delta 18O seawater is at marine isotope stage 22, and then we see continuously deep glacials after that. So even in the Pacific, although the bottom water temperatures are near freezing for the mid-Pleistocene transition, we calculate out delta 18O seawater histories that are very different. And similarly, during these glacial periods, we're seeing this bottom water temperature warming when we expect, or I would think it's a glacial period, you might expect that you would actually have cool bottom water temperatures, but in this case, we actually have warm temperatures. So throughout this interval, we're seeing that we have different delta 18O seawater histories, depending on which ocean basin we look at and where in that ocean basin we look. So in the North Atlantic, our delta 18O seawater is relatively flat. There's no implied increase in ice volume over the mid-Pleistocene transition. If we look at the Pacific, we have kind of these two excursions at marine isotope stage 22 and marine isotope stage 16. But overall, we do have an apparent increase in the delta 18O seawater. And if you look at the South Pacific, again, we have a large step in the the delta 18O seawater here at marine isotope stage 22. That implies we had a large persistent growth in ice volume after marine isotope stage 22. So, which is it? We obviously have many regional histories depending on which ocean basin we're looking at. So this kind of one of the challenges I think that we're having, or not a challenge, but one of the things that these records are telling us is that there was some change in definitely the character of the water that was going over these areas that's related to regional change. But one of the other ideas that has been proposed is that you had a really big change in deep ocean circulation at this time. So prior to the 900 kiloyear event or the marine isotope stage 22, the neodymium records that we have, at least the way that they're being interpreted right now, is that you had a very strong North Atlantic deep water during glacials. And then after the 900 kiloyear event, we start to get into a situation that looks more like the glacials that we have today. So for instance, in the last glacial maximum, it seems that we have a less spatially extensive North Atlantic deep water during glacial times than we do during the interglacial today, right? The interglacial NADW is really strong, but it seems like during the last glacial maximum, the spatial extent of the North Atlantic deep water is reduced in comparison. So if we think about the North Atlantic deep water, we're seeing an increase of probably cool North Atlantic deep water over the mid-Pleistocene transition. And then the other thing that we see for our South Pacific records is that the particular area that record was generated seems to be sensitive to changes in water mass boundaries. So when you change the configuration of the prevailing water masses, it's going to give you a different signal. So, you know, this is one of the challenges with looking at an individual site and using it as indicating full kind of global history. And that brings us back to the power of stacking these kinds of records. When you use a stack like LOR4 prob stack, you're essentially averaging out these regional differences to get you to this more global signal or a record of global change. And so that's kind of essentially what I did with these delta 18O seawater records that were available from these three different sites. When you have regional differences, you basically create a stack. And so, you know, this is a kind of a statistical process, but basically what I did is I used Thermohaline has a really nice package, PSU solver, that lets you propagate errors when you're calculating temperature in the delta 18O seawater. So I took the original records, I interpolated them, I bootstrapped them to kind of get a full understanding of the errors and the averages and create a stack of the delta 18O seawater over the mid-Pleistocene transition. So, and then using this as an approximate estimate for global sea level or ice volume, essentially. So if you stack the delta 18O seawater, you're getting towards a global sea level or an ice volume curve. And so if you look at that record over this time period, on this axis is just LOR4, on this axis is the sea level or the stack that I've created, and on the horizontal axis you have age here. And when you stack all these records, basically it seems like you have two steps in the delta 18O seawater, or two steps in sea level drops over the mid-Pleistocene transition. You have one at marine isotope stage 22, and then you have another one at marine isotope stage 16. So overall, it does appear that you're getting ice volume increase over the mid-Pleistocene transition. You can look at, and in terms of thinking about CO2 as the driving force of this, this is one of the reasons that I'm really excited about the EPICA, Beyond EPICA effort and I know that Tom talked about the CO2 records that he's been working on using boron isotopes, but it really will give us an opportunity to kind of think about how CO2 is related to maybe the North Atlantic cooling that we're seeing and these changes in ice volume over the mid-Pleistocene transition. So it seems, given this change in delta A2 seawater, we might have changes in ice sheet dynamics. One of the challenges that you have with these records is that you can't tell which ice sheet is doing what, but there are some ideas that have been put out by other people in terms of which ice sheet is changing over these different time periods. So one idea for the marine isotope stage 22 900 kiloyear event is that maybe Antarctica was the source of this change at marine isotope stage 22. So we know during this time that southern insolation was anomalously low. The sea ice extent was much more equatorward, and we see there seems to be changes in the ice sheet sea ice dynamics during this time. And another idea that's been proposed by Mary Ramo is that you transition from marine-based margins in Antarctica from continental margins before. And so you can imagine this change in Antarctica impacted these deep water formation areas, and that's why we're seeing these signals in these benthic records. It seems possibly that marine isotope stage 16 was related to changes in North America. Some ideas that have been proposed. We know that there's large ice rafted debris in North America during this time, the so-called iceberg armadas. And so maybe this is related a little bit more with the ideas presented by Peter Clock. Is it you're going from kind of slippery ice sheets to more stable ice sheets that allows them to grow a bit more. And again, this would impact the deep water formations in the North Atlantic. So just to summarize the ocean circulation story that we have over in the mid-Pleistocene transition, we do see that there's North Atlantic bottom water temperature cooling over the mid-Pleistocene transition and prior to the 900 kiloyear event. Was that forced by CO2? I hope the ice cores can help us answer that. We see that there's complicated regional delta 820 seawater histories and big climate events that happen at marine isotope stage 22 and marine isotope stage 16. And our new delta 820 seawater stack shows that marine isotope stage 16 and marine isotope stage 22 are times of apparent ice volume growth. So with that, obviously this is takes a lot of effort, and I'd like to thank my co-authors, including Maureen Ramos, Cindy Associan, and Yair Rosenthal, and the funding that I received from NSF and the Columbia Climate Center for this work. And I'll take any questions that you might have before we head on to Alfredo's talk.
Thanks a lot. Thanks a lot, Heather, for this interesting talk. Yes, as Heather said, the floor is open for questions. You can